Yes. Well, did you look at the agenda for the week?
I didn't see it.
So it's not this week.
It's going to be next week.
Probably at some point. Haven't scheduled it yet, though.
All right.
Okay. Yes, Joe?
Are we going over homework?
Sure.
Can you do for homework 3? Can you go over the first one? I wasn't here. I was a little confused.
Sure.
Thanks.
Okay. So here we're asked to do a bunch of things, right? We're asked to write down the domain and then the intervals of positive, negative, 0, increasing, decreasing, and constant. So we'll start and just kind of take these one at a time. When I write my intervals, I'm going to write those using the interval notation. I think it's the easiest one to use. So for the domain, what I'm going to be concerned about are the set of x's. So I'm going to locate the farthest left point on my function, which would be right here. And then the farthest right point on my function, which would be right there. And I noticed that in between those 2 points, everything is connected. Like there's no gaps or jumps or anything. So my domain is going to start at that x-coordinate of -6 and end at the x-coordinate +5. Now, because there is a point in our function that uses the x-coordinate of -6, it's that far left point. That means I use a bracket. And because there's a point on my function that uses the x-coordinate +5, that's going to get a bracket also. Okay with that?
Yeah.
Okay. So now I'm going to do the range. So I'm going to locate the lowest point on my function, which would be this one, and then the highest point on my function, which would be this one. Now the range is about the set of y-coordinates. So my lowest y-coordinate is -2.5, and my biggest y-coordinate is +3, and I notice in between those the graph is connected all the way through. There's no jumps or gaps or anything. So I can just kind of, everything in between is covered. So I notice I do have a point that uses the y-coordinate -2.5. And I do have a point that uses the y-coordinate +3. So each of those get a bracket. Okay with that? Okay. Next up is positive, -0. So the positive part of the graph is the part that's above the x-axis. So that's this part here, and then this part here. Agreed with that? Okay, so when we write these intervals for positive, -0, or increasing, decreasing, constant, we're always describing the location of the graph, which really means we're using the x-coordinates. So if I look at that positive part, the first positive part begins at the x-coordinate -5. So it begins at this point here, -5, 0, and ends at this point, -1, 0. Now I need to look at those points that correspond with the -5 and the -1. I need to determine whether those points are above the x-axis or not. If I look at them, they are not above the x-axis. They are on the x-axis, right? So they should not be included with the positive parts. So I'm going to use parentheses for those. And then I'm going to look at the next part of my graph. So I'll have that little union symbol to connect the two parts. That begins at the point 4, 0 and ends at the point 5, 3. If I look at the point 40, that is not above the x-axis, so the 4 gets a parenthesis. But if I look at the 5, or the 0.53, that point is above the x-axis, so that gets a bracket.
So when the points are above the x-axis, they give you the bracket.
For positive,
For positive.
because positive is talking about the stuff that's above the x-axis.
Okay.
Right? So this point here, the end point, is above the x-axis, so it would get a bracket. Similar for negative, except now we're interested in the stuff that's below the x-axis. So we have a negative part here and a negative part here. Agree with that? Okay, that first negative part begins at the point -6, -2.5. And it ends at that point -5, 0. Now, if I look at that point -6, -2.5, that is below the x-axis, so that gets a bracket. But the point -5, 0 is on the x-axis, that gets a parenthesis. And then I'll use that union symbol to connect to my next interval. That next interval begins at the point -1, 0 and ends at the point 4, 0. And each of those 2 points are on the x-axis, so they both get parentheses. And then I need to do the zeros. So I have a 0 here, a 0 here, and a 0 here. That's the place where the graph is on the x-axis. Notice that this situation is different than the previous two for positive and negative, because in the positive and negative places, we had an infinite number of points because we had a connected part of the graph. Here we have distinct individual points. So the notation I would use to describe the 0 set is going to be different. I'm going to use the set notation where I'm just going to list the individual items. So the individual x values I have are those 3. Hi. Jacob Dutz, for you. You're welcome. Is that okay so far, Joe?
Yeah.
Okay. So now I'll erase all this stuff, and now we're going to talk about increasing, decreasing, and constant. So increasing is where you're walking uphill along the graph. So we always talk about increasing, decreasing, and constant, moving from left to right across the graph, just like you read. So if I look at the uphill parts of the graph, that part is uphill. And then that part is uphill. Agreed? Okay. So the uphill part begins at -6, -2.5, and ends at -3.27, comma 1 point whatever. So we have -6, comma -3.27. And for increasing, decreasing, constant, we're always going to use parentheses. There's no brackets really ever for these, and it has to do with the way that we define increasing and decreasing and constant from a really technical perspective. I don't need you to know the technical definition. I just want you to remember that we use parentheses for all of those. Okay. The next section, it begins at 1.94 and ends at 5. And again, all parentheses. Okay there? And then we have one decreasing section. That's the part where we're walking downhill. So that goes from -3.27 to 1.94. And again, always parentheses for these. And then the constant sections would be like the flat parts of the graph. I don't see any of those. So I'll just write none there. You could leave it blank. Either is okay. Does that feel okay there, Joe?
Yeah.
So in general, there's nothing super tricky to doing this, right? Like you're just looking at a picture and kind of using the notation to describe what you see. Probably the most difficult part is you getting used to using that notation, right? When to use a bracket, when to use a parenthesis, like remembering that your intervals for increasing, decreasing, constant, positive, negative, zero always are using the x coordinates and not the y's and stuff like that. But the actually writing of this stuff down, like we didn't do any calculation. All we did was use our eyes and looked at what we saw and used the notation to describe it. So it shouldn't be too bad there. Other questions from the homeworks or whatnots? Yes, Megan, thank you. The mid-chapter review? Yes. Okay. So I say assume there's arrows at the end of the graph. So we're asking about number 7 here specifically. Like what do we expect these arrows to be doing here at the end of the graph, right? So I wasn't very clear about what these arrows would be doing, right? It's kind of ambiguous based on just assume there's arrows at the end and you're given this picture, right? And that's probably a poor job on my part because I didn't probably give you enough information here for you to reasonably assume what's going on. So I would, at this point, if I'm looking at this homework assignment or this kind of a question, I wouldn't allow you to kind of interpret this however you wanted, since I didn't give you enough to really for you to know definitively like what are those arrows really doing? Are they going flat? Are they going up? Are they going down? What's going on there? Perfectly reasonable question to ask. And as a result, I would probably take almost anything you gave me that was using a notation effectively that demonstrated you understood what was going on. Now, what I had intended was for you to assume that this just kind of keeps going, doing the same thing forever in both directions. Now, I don't know if that was the assumption that you made when you looked at this or not. Probably not. Now that you point out what's going on here and that it wasn't super clear to you, I can see exactly that, like, oh yeah, that wouldn't have been super clear. That would have been what I was intending, although if you didn't make that assumption, like, that is not your fault. That is my fault for not being clear enough as to what was going on there, describing it for you guys. Do you want to talk about this one with the way I'd intended it, or no? Okay, so let's assume that we saw this and interpreted it the way that I intended, although the chances of that happening are probably not great. And again, not your fault. Okay, that was my issue for not being clear enough on that, and I apologize. Okay, what were we being asked to do here? A bunch of things, right? Okay, so basically the same question as what Joe had asked, right? With the addition of we're doing end behavior here also. Okay with that? Okay. So the domain, if I'm assuming it's kind of going in both directions, the far left point and the far right point are both infinite, right? So the domain here would be just from negative infinity to positive infinity. Now the range is not going to be infinite, because if it's just repeating itself over and over and over again, the lowest we get is like this value, which looks like maybe -1. And the highest we get are the top of these peaks, which looks like maybe +1. Okay with that, Megan? So I would say the range here would be with a bracket, -1 to +1. Okay. Okay, so next we need to do positive, negative, and 0. Okay there? For what's up next, all right. So if I look at the positive part, I see that this is going to have infinitely many positive sections, right? So how would you do the notation on this that's not entirely clear? Let's talk about what would be a reasonable thing for you that you could have done that would have been okay, or that I would have accepted. So this, right now, we see a positive piece right here, right? And there's some other positive parts that we can see, but the big observation that I would hope that we could make here is that this graph is really like a bunch of identical segments just repeating itself over and over and over again. So what I would say, if this thing is going to it has infinitely many of these positive sections, is I'm going to just describe the location of one of the positive sections and then say this also happens every blah, blah, blah units. So this first section, it looks like we're going from 0 to, I don't know, maybe 3 seems like a reasonable estimate there. Actually, we can tell it's not quite 3 because the next one happens a little bit after 6. Maybe let's call that 3.1. Okay with that. And then I would say, and every, I don't know, like 6.2 units before and after. So by that I mean that if I add 6.2 to each of these, I would get another positive interval again. Now there's a symbolic way to describe this, but I'm not interested in you guys being able to do that right now, or really in this course. Not interested in you guys being able to do that. So we'll just do that with words. Is everybody okay there? We can make the similar argument from a negative perspective. Like if I look here, there's a negative, and there's going to be, again, infinitely many of these negative sections. So this looks like negative 3.1 to 0. And then we'll say every 6.2 units before and after. And then I have, again, like we're going to have infinitely many of these 0 parts, right? So I'm going to say, well, we have this one specifically at 0, 0. We can actually do this notation. The set of x is such that x equals 0 and every 3.1 units before and after. And do it that way. We've seen that notation before, and that would be a reasonable thing you could do. Is this okay so far, Megan? Okay. So I'm going to erase my highlights here on the graph real quick so we can do the increasing, decreasing constant part. And again, for those of you that are following along or watching this and are kind of freaked out, this is far harder than something I would ask you to do on a test. Okay, so just, I think that first one that we did together that Joe asked about would be reasonable. I think the previous 2 on here would be reasonable test difficulty questions. This is, I think, more complicated than something I'd expect you to do on the test, since we hadn't ever done an example like this in a homework assignment before. But that's okay that we put tricky things in the homework, because again, the homework isn't graded on correctness, and it gives us the opportunity to talk about things like this in class, which is what I'm hoping happens. Okay? So you're doing the right thing about asking about this, and certainly even if you want to ask, like, is this something, would you expect me to be able to do this on a test? Like, those are reasonable questions to ask, and I'll, for the most part, try to be very clear about, like, what level of difficulty I would expect you guys to be able to handle in a test setting versus, you know, like a non-test setting. Okay. Increasing, decreasing, constant. So if I look here, I see like an increasing section right here, right? Where we're going uphill. But again, there's going to be infinitely many of those. So I'm going to describe it kind of similarly what we did before. So this would be like, looks like negative 1.55 comma negative 1 would be this point down here. And let's call this point positive 1.55, positive 1. Why'd I pick point 1.55? Because we called this whole section 3.1, so if it's halfway, half at 3.1 is 1.55. Again, if you estimated those to be something a little bit different, like clearly I didn't give you specific points here, you would have had to make your own estimates there, which would have been fine. So we're going to go from negative 1.55 to positive 1.55. And then every 6.2 units before and after, right? So here, yeah, that's right. And then our negative, let's say we are going to do that one. So that's 1.55 to like 4.15, I think. If I did that arithmetic correctly. And then hopefully it's easy to see that there aren't any constant sections on this graph. There's no flat parts. At least from the way that we talked about how I was hoping you'd interpret it, although looking at this again after Megan's questions, chances of that were probably pretty slim. Does that feel better? Okay. Yeah, Joe. Oh, sure. So on this one, the end behavior is supposed to give you an idea of like how the arrows are pointing at the end of the graph. So if we catch like this part of it, it seems like the arrow is pointing down, but if we catch that part of it, it seems like the arrow would be pointing up. And it's not ever pointing to a specific value because it keeps just jumping back and forth. So what would we say about the end behavior here? Is the arrow pointing to anything specific? So can we say anything about the end behavior? Yeah. There isn't any. This kind of graph is called an oscillating graph. Where it just goes back and forth between some values. You'll see this kind of thing happen next year in trig and precalculus if you take that course. So this one actually has no end behavior because, again, the arrows don't settle down towards any specific pattern. They're just kind of continually, sometimes they're going up, sometimes they're going down, sometimes they're going up, and then sometimes they're going down. So what's it doing at the end of the graph? Can't really say. because it could be going up or it could be going down. We don't know. Okay there? And these are good ones to ask about. I'm glad that you guys have been asking about these sorts of things. Like this is definitely, we'll be asking you to do, these kinds of questions on the test. Obviously not something as ambiguous as this particular question, but certainly should be able to do domain and range and increasing, decreasing, constant, positive, negative, zero. Should be able to do that kind of thing, similar to what our the first question that Joe asked about, or the previous two on this sheet, I think are all an appropriate level of difficulty. Anyone else? Yes, Megan? 8 and 9. Oh, okay. Let's see. This emulator is so laggy that it doesn't always pick up your keystrokes if you're not watching. It's very irritating to me. All right. So looking at this, it appears that we have one local maximum and one local minimum. They're hard to see on this one because they're so close together. So one thing we could do is we could readjust our window so we can see this part that we care about. So if I look here, it looks like it's maybe from everything we care about in this section is from 0 to maybe -5. And on the y direction, maybe from -2 to +2. So if I go to the window here, I'll change the graph paper a little bit so it's easier for me to see. You didn't need to do this. I'm just going to do this so it's easier for us to see what's going on. And by doing that, I have a much clearer picture of what I'm looking at, which makes doing the left bound, right bound guess a little bit easier to do if you're having trouble with that. So I'll do second and trace. I'll do the maximum first. So somewhere left of that maximum, that looks good. Then somewhere to the right of the maximum, that part, that looks good. And then I guess I didn't even need to move it. So my maximum here is -2.577, comma 0.385. And then the minimum would be, well, that's left of it, I guess. And then we'll have a little trip here to get to the right. Okay, that's fine. And there's my guess. And then the minimum would be -1.423, comma -0.385. You're welcome. Did you get them? Good. Again, not difficult to do once you feel like you're comfortable with the graphing calculator, right? Getting the calculator to do what you want it to is the hardest part, but actually using it, like there's not much that you have to give the calculator. And just kind of remembering where the buttons are and how to get to the menus and the order to do things. And the actual mathematics involved for you on your end is not much, right? Okay. Cool. Any last questions from any of this stuff? Okay. Very good. If anybody changes their mind, let me know. We can always circle back to something here. But in the meantime, let's move on and talk about our last topic for this chapter. So our last topic here in this chapter is going to be about transformations of functions. And what I'd like to do is have you guys think back to geometry for a few minutes here. In your geometry class, you talked about transformations last year. There would have been 4 types of transformations you guys would have talked about. Does anybody remember any of those 4? Two of them start with an R. Let me get you started here. There's a reflection. Yes. Rotation would be the other one that starts with an R. Yeah. Anybody remember one of the last 2 here? One of them starts with a T. Close, it's a translation. And the last one starts with a D. I think this one you spend like almost, I think there's a whole section built around this one when you do similar figures. It's a dilation. So in any of your high school courses, we're not going to worry about rotations of functions. So we're just going to ignore that. We need a lot more powerful mathematical tools than what are available to us as a high school student to be able to talk about those things reasonably. But let's talk about these other ones. So there's 2 types of reflections that we'll really talk about. A reflection across the x-axis and a reflection across the y-axis. So back when you were in geometry class, if this was your pre-image, would be like some little triangle or something, right? If we reflected across the x-axis, the resulting image would be something that looked like this, right? It's the exact same triangle, but it's in a new location with possibly a new orientation, right? Or if we reflected across the y-axis, where the red one is still our pre-image, the result would be something like this. Again, new location, and a possibly different orientation, but still the same relative dimensions, right? Everybody kind of remember doing that? Okay. For a translation, we really talked about 2 types here. So we talked about shifting left or right, or shifting up or down. So say you moved like 5 units to left and then like 3 units up. You know, you'd end up with your triangle in a new location, but the orientation stays the same and the relative dimension stays the same. You guys kind of remember doing that? Okay. For a dilation, again, I think when you guys in geometry always talk about a symmetric dilation where you are scaling the x and y coordinates by the same factor, you don't really need to do that. So we're going to have things that we do vertical, and there's dilations that we're going to do horizontal. So say here's our triangle. If I do like a vertical dilation, it'll like get it, you know, like stretching up, or maybe you're shrinking down. I didn't draw that triangle big enough to really shrink down, but the blue there is a vertical. A horizontal would be like stretching things horizontally. So maybe you pull it this way, like stretching out from left to right. So the height doesn't really change, but the width does. I think when you guys did geometry, you did all your dilations were in both directions at the same time. But we really don't need to restrict it to that specifically. We can be a little bit more general. Now, certainly you could stretch the same amount in both directions. There's nothing wrong with doing that still, if thinking about them as two separate types of dilations, right? If I stretch by 2 and then stretch by 2, it's going to be the same result as stretching both directions by 2. Everybody okay with that? Okay. So hopefully that feels like kind of familiar, right? Even if you don't remember how we go about doing that, visually you should remember kind of what those things look like, I hope. And that's all I'm really trying to do, is kind of connect this to an idea that we've already seen before, so it doesn't feel very foreign, although we're going to apply it to a function rather than a shape, which is, I think, primarily what you did with this stuff in geometry, right? You took some points or a shape or whatever and then did the transformation to it. But remember our definition for a function. A function is just a set of ordered pairs, right? So a shape is just a set of ordered pairs. So anything I should be able to, any transformation I can do to a shape, I should also be able to do to a function. Everybody with me there? Since they're basically just, both of them are sets of ordered pairs. The biggest difference is, with a shape, you can often get away with just describing it using the vertices, right? Like if you have a triangle, the only points you need to know are the 3 vertices, and you can draw the triangle. You don't really need to think about it as an infinite collection of points, right? For a function, though, you kind of need to think about it as an infinite collection of points, which means the notation that we're going to use to kind of describe these transformations needs to adapt a little bit so that we're able to, describe the same thing, but in this different context. Okay with that idea? Okay. So, in geometry, we talked about a pre-image and then an image, right? So the pre-image was like the thing before you did the transformation on it, and the image was the thing that you got after the transformation. In algebra, we have a parent function, and then we have the resulting transformation. So those two, it's just a different piece of vocabulary that's really kind of describing the same thing. So in geometry, when we described this pre-image to image, this transformation, we did something like, we used like a little transformation map like this, where we had described how the x and y coordinates were changing to go from the image to the pre-image, or the pre-image to the image. Do you guys kind of remember those things? Again, how to use them exactly or how to construct them, not that important right now. I'm just trying to jog our memory because I'm connecting these new ideas to hopefully something we kind of remember about, so it doesn't seem quite so foreign. So in algebra, our parent function would be some y equals f of x, and our transformation is some g of x that is equal to this transformed version of f of x. Now this form is quite important. This course really becomes a survey of these different types of algebraic functions. So each kind of chapter, unit, or whatever you want to call it, we're going to be studying kind of a new, different algebraic function. But what doesn't change each time is the general form of each of these functions, which is this transformation that we're looking at right here. So what we're going to be able to do here is eventually, by looking at the form of our function, be able to immediately look at it and be able to tell certain attributes about it. Like, how is the parent function changed in this particular transformation? So this is important. You're going to want to make sure you know that form, because it's going to come up over and over and over again throughout a lot of first semester and most of second semester. We'll see this over and over and over again. So it is something that you're going to want to be familiar with enough to where probably end up memorizing it. It doesn't have to be done immediately, but it's going to be something that'll be important to doing this next homework assignment, and be something that's important in future chapters. Okay? So these values here, these A, B, H, and K, all inform us about the transformation that's occurring. So each one of these A, B, H, and K are going to tell us information about the type of transformation that's occurring. So when A is positive, actually let's start negative. We're going to have a reflection across the x-axis. When A is positive, we have no reflection across the x-axis. So one thing that A is in charge of is it's describing one kind of reflection. a reflection across the x-axis. If the magnitude of A is greater than 1, when we put the absolute values around something, we're talking about the magnitude, just the relative size of the number, not including its sign. That's going to describe a vertical stretch by a factor of A. So the A is in charge of two things, right? It's in charge of reflection across the x-axis and a dilation vertically. If the magnitude of A is less than 1, this is going to be a vertical shrink by a factor of A. And if the if A is just, the magnitude of A is equal to just 1, there's no vertical dilation. Okay here? So if the B is negative, here we'll have a reflection across the y-axis. And if the B is positive, we'll have no reflection across the y-axis. If the magnitude of B is greater than 1, we'll have a horizontal stretch by a factor of B. And if the magnitude of B is less than 1, we'll have a horizontal shrink by a factor of B. And if the magnitude of B is equal to 1, we have no horizontal dilation. So just like A, that B coefficient is in charge of two things: a reflection across the y-axis and then a horizontal dilation. Next is H. So if H is positive, we're going to have a translation to the right, H units. If H is negative, we'll have a translation to the left, H units. And if it's 0, there's no horizontal translation. So the H is in charge of only one thing, whether you're translating left or right. And the last one is K. If K is positive, we have a translation up K units. If K is negative, we have a translation down K units. And if K is 0, we have no vertical translation. Okay. So, little example here. So we're asked to describe this transformation. The first thing that I would do is I would try to rewrite the transformation that I've been given so that it's in this general form. So it's easy for me to identify the values for A, B, H, and K. Everybody's okay with that plan? So I have a -2 out front. But notice here, I don't have anything where the 1 over b is, right? So what number is there that we wouldn't have written down, but we know is actually there? A 1, right? And I can write the number 1 as just a fraction 1 over 1. So we'll do that. Is everybody okay there? Okay. Next thing I'm going to notice here is that mine I have a plus sign, but here I have a negative sign. So how do I rewrite a plus sign as minus something? I have +3, I need to write it as minus something. It's the same thing as minus a -3, right? So do that. Oh, I don't know why I put 5 there. It should have been a K. Okay, now we've done the hard part. So I can see that the A is -2, the B is +1, the H is -3, and the K is 5. Is everybody okay with how I determine those values? Just by kind of using that general form. Now that I've identified the values for A, B, H, and K, I can go back and use that list of criteria that we just wrote down to determine the type of transformation that's occurring. So since A is negative, that tells me that we have a reflection across the x-axis. And since the magnitude of A is greater than 1, we have a vertical stretch by a factor of 2. Everybody okay so far? Since B equals 1 is positive, we have no reflection on the y-axis. And since the magnitude of B is 1, we have no horizontal dilation. Since my H is negative, we will translate left 3. And because equals 5 is positive, we're going to translate up 5 units. Is everybody okay here? So we'll say this is part A. I'll call this part B. So let's say that we have the graph for the graph for f of x is this. And we want to then graph that g of x. So to do this, I'm going to use the transformation map form from our geometry class. So remember how up here, I'm going to use that as my tool. Okay? So we have xy goes to bx plus h, ay plus k. Now from before, we knew b was 1, h was -3, and 5, right? So if I fill those in, my map is that. Everybody's okay there? So all I'm going to do now is I'm going to just apply that map to each one of the points, or the 3 key points, I should say, for my function that I've been given. So my first point becomes -2, 5. And my second point becomes -1, -5. And my third point becomes 0, 5. So if this was my original, I have -2, 5, -1, -5, and then 0, 5. So there's my g of x.
Thank you.
Thank you. Braylon, for you. So if we were to compare these two graphs using the vocabulary that we just used, well, it definitely appears that this has been shifted to the left and then shifted up, right? It seems like this has been stretched vertically. See how it's taller and skinnier? And it's flipped upside down. That's the reflection across the x-axis. So we see that what we're looking at here from a graph is supported by the verbal description that we found earlier, right? Can you guys see that? So it should all match up and reinforce itself. What do you guys think? Do another? Sure. Let's say that this time our transformed function is Okay, so we're going to describe this transformation in words and then draw its graph, okay? So the first thing I want to do is I want to rewrite this so that it's in that form. That we talked about before. To do that, is there really much to do? Yes.
What's the y? The one.
-1. 1, -1. So to rewrite this g of x in the same form, there's not really anything to do, right? The only thing that we have to remember is that the b is just 1 in this case since there's no coefficient on the x. Everybody's okay there? So a is 1/2, b is 1, h is 4, and k is 5. What are we noticing about the values for h here? I go back and I look at the previous one. Appears to be the opposite of what it does in the function, right? So keep that in mind. That's the single most common mistake students make when dealing with this is goofing up the sign on their value for h. So please be careful there. Okay. So let's just write down the description of what happens and then skip the stuff that doesn't do anything rather than writing down like doesn't do anything. So the A, what do we get from the A? Do we get any reflection? No, because it's positive, right? Are we going to get a dilation? Yes, because its magnitude is not 1. Okay? So since the magnitude of A is less than 1, this is going to give us a vertical shrink by a factor of, well, whatever. The B, now, does this cause a reflection? No, because it's positive. Is it going to cause a dilation? No, because its magnitude is 1. So that didn't do anything at all. Now let's go to the H. Is the H going to cause a translation? Yes, because it's not 0. Since the H is positive, which way is the translation going to go? It's going to go to the right 4 units. So remember, the H goes left and right, and the K does the up and down. Is the K going to cause a translation?
Yeah.
Yes, since it's greater than 0. So which way is it going to go? Up 5. Is everybody okay there? And then when you guys are doing your homework or whatever, you can skip writing down the things that don't do anything. You can just write down like we did here. I didn't include anything about the reflections because no reflections were happening. It's okay if you just wanted to skip those. Okay? Let's draw the graph now. So again, to draw the graph, I'm using this transformation map. And when I fill in my values then for A, B, H, and K, I have this. Everybody's okay there? Now I just have to remember the points from the other page. If I don't get them right, if somebody can double check me. But I think these were it. Good. Whew. Okay, so now all we have to do is plug these points in to get our new points, and then graph them, right? And that's negative 1.5, so when I add 5 to that, I get positive 3.5. Everybody okay there? So I just did those calculations quickly and in my head. Of course, if you need to use a calculator to pound those out, that's okay. No big deal. This as our, our original. I'm not going to be able to fit it there. Hold on a second. Okay. So there's 2, 3.5. We have 4, 5. And then I have 5, 4.5. And I have, 4, 5, excuse me. And then I have 5, 4.5. And then 6, 6.5. So it looks like this. So you can see that we've moved things over and up, right? And it's gotten a little bit squished down. It's not quite as tall as it was before, right? What do you guys think? Joe?
I have a question. Can you scroll up a little bit?
Absolutely.
So yeah, I understand the -2, 3, and like below that, just like solving it. But for the x and y above that, where it's like x equals 4, 1/2, 5, yeah, that. So do you get the 4, the 1/2, and the 5 from the k? And all
Yes.
those values?
Yeah. So this, in this formula, the b, h, a, and k are the same b, a, h, and k.
And you just plug those in.
You just plug the same values in. Yep. Exactly right. Is that cool?
Yeah, thanks.
Okay. Yeah, no problem. Again, that's an important question, right? Like if you don't know where those numbers come from, this makes a lot less sense. But it's the same A, B, H, and K. That's why I use the same letters in the two little equations there, formulas. Okay, this was the last topic that I wanted to talk about in this first chapter. I'll have a review assignment for you guys that I'll post both to PowerSchool and to the content library later on today. I have to double check to make sure it's finished or whatever. Next time we meet, we will take any questions from that review. If you have them, talk a little bit about what the test format you should expect, and then talk about the next chapter. We'll start that, and then we'll do the test the following class period. Okay, so that's next week on whatever, I don't know, it's whatever day it is that we meet first time next week. I'll get that on PowerSchool also for you guys. Okay? Everybody feel reasonably okay with how things are going? If you don't, come see me. I'll be happy to help. But I can't read your minds. So if things aren't going well and you need to ask some questions and get some clarification and for me to give you some more feedback on what you've been doing or whatever, come find me. I'll be happy to help. Okay? All right. We'll see you guys Friday.